Right, this time we're going to look at how to actually measure the Planck constant. Now, I'm going to remind you of something that you will have seen at GCSE. If you did an experiment looking at, which you should have done, looking at the current voltage characteristics of different components, you will have seen with an LED that obviously nothing happens in the negative direction. That should be along the axis. Nothing happens in the negative direction because it's a diode, so it doesn't allow current flow in the opposite direction. And then in the positive direction, you will have noticed that nothing happened for a little bit, and then suddenly it started to increase like this. Now, it is this here and this section that we are particularly interested in today, because this voltage here, this potential difference at which the LED suddenly starts to allow current to go through, this is known as the threshold voltage, okay? And this here is what today's session is all about. Now, I'm going to explain to you why this is. Now, the reason behind this is because we have to remember that we're talking about quantum physics here. And in quantum physics, everything is about individual particles. So what we need is, we're saying that we've got an LED which is creating light. Now, that means that LED has to create many times individual photons. So it's not just creating light at a certain wavelength, it's creating lots and lots of individual photons of light. And each one of those photons of light has a certain amount of energy. And the same thing goes in the electric current that's going through the LED. As if we've got our LED, we'll just remind ourselves of the symbol here. We've got an LED, we've got electrons that are going through, this is actually a conventional current, so the electrons are going that way, but I'm just going to imagine the electrons coming through. So we've got our electrons coming through the LED, and as an electron goes through, that electron is going to lose some energy, and that energy is going to be turned into a photon of light. If we remember our definition of potential difference, if I say that I have a voltage across here, you will remember from looking at potential difference and EMF that the EMF, the electromotive force, is work done on the electrons, okay? Whereas the potential difference is work done by the electrons, okay? So an electron comes in, I'll draw it the correct way. So an electron comes in and it goes through this direction, and that electron has a certain amount of energy, and it is going to use up that energy as it goes through the LED. Now, the key thing here is that because we're talking about quantum and we're talking about individual particles, each one of these electrons has to have enough energy to create a photon of light. So what we can't have is let's say, for example, the photons of light that are coming off, just put some random numbers in here. Let's say the photon of light coming off has 3 electron volts of energy. What we cannot do is we can't have 3 electrons each with 1 volt. This will not do the job, okay? This will not do the job. We need to have each individual electron must have, this should be, I'll say electron volts here because we're talking about energy. Each individual electron must have enough energy to create that photon. Otherwise, nothing is going to happen. And that is the key idea here. Now, I'm going to show you an experiment that uses this whole idea here. Now, as with all good A-level experiments, I'm going to show you that there is like a single calculation you can do from one measurement, but really we're going to try and do multiple measurements. We're going to plot a graph and we're going to do something with a gradient. So, first of all, let's draw, I will rub this off because I'm going to make use of this space. First of all, let's draw the circuit diagram that we're going to use. Now, what we're going to be doing is we're basically going to be turning the voltage or the potential difference across an LED. We're going to be turning that up very slowly until we just see light coming off, so we know we have the threshold voltage. So let's have a look. You could have some kind of cell or battery up here. this is going to be connected to a potentiometer. You could use a variable power supply or any kind of system that allows you to vary the voltage across an LED, but generally the potentiometer is favoured because it gives us the full range of voltage. This is then going to go through my LED here. I've drawn that so elongated, and that's going to come to our potentiometer. There's option you could put a safety resistor in here. Most of the diagrams you see for this will have an extra resistor in here, but I mean, it's for the terms of the physics behind it, it's not really needed. It's just to protect your LED from breaking. If you were to make sure you've got low voltages, you're probably okay. And we're also going to need to know the voltage or potential difference across our LED. I'm not actually interested in the current, ammeters or anything like that for this experiment, because I don't care how many photons are being emitted. I don't care how many electrons are going through. All I care about is how much energy does each electron have as it travels through our LED. Okay, so if we look at our equations, we're going to say that the work done by each electron, okay, so the work done is charge times by voltage. So as an electron goes through this LED, the work done by that electron is equal to the charge on one electron, which is 1.6 times by 10 to the minus 19, multiplied by the voltage that we have across here, okay? So what we're going to be physically doing then as we do this experiment is we're going to increase the voltage across here using our potentiometer, or like I said, you could potentially use a variable power supply, but we're going to slowly increase the voltage until the LED just comes on. Now to do this, what you would probably have is you would have an LED, and then you would have a tube of like black card or paper or some kind of black tube, so you can physically look down that tube at the LED with no ambient light, okay? So you can look down the tube at the LED, and just at the point that it just comes on, okay, that is the point that we're going to record as our threshold voltage, okay? That is the point that at that voltage, a single electron going through this LED has just enough energy to create a photon of light to come out from that LED. So yeah, we could do a single calculation now. So once we've got that, let's just say, for example, that we've done our experiment here and we've got a threshold voltage, and we said the voltage is equal to 1.8 volts, for example. Now, I could already say in my head, I could already tell you right now that the amount of energy that equates to is 1.8 electron volts, because that is the definition. Okay, so 1.8 volts of energy on one electron, 1.8 volts of potential difference on one electron is 1.8 electron volts of energy. But we are going to be working in joules, so that we can do our calculations here to get the Planck's constant in joule seconds. So, if we look at our equations there, so the amount of energy that electron has, if this was our answer here, okay, this was our threshold voltage, we'd say the amount of energy, it would be equal to 1.6 times by 10 to the minus 19, the charge of an electron, multiplied by 1.8 volts. That is the amount of energy that electron has lost as it has dropped across its 1.8 volts per coulomb of potential difference. 1.8 joules per coulomb of potential difference. So we'll do this calculation. I should have chosen 2 really, shouldn't I, make it easy? 1.6 times 10 to the minus 19 times 1.8 equals 2.88 times 10 to the minus 19. 2.88 times by 10 to the minus 19 joules. Okay? Now, yeah, we could do an individual calculation now, because we know that this is the amount of energy that the electron, I'm repeating myself a lot of times here, but this is the amount of energy that the electron has lost as it's gone through the LED. And because this is the absolute minimum amount of energy that electron can lose to create a photon, we know that this is the amount of energy that that photon has. So we're going to say that then this energy of 2.88 times by 10 to the minus 19 joules is equal to H times by C over lambda, or HF. Now, the important thing that we need to make sure we know here when we're doing this experiment is we need to know what is the wavelength or frequency of the light coming off our LEDs. Now, this is something that you would find from the manufacturer, okay? So either it would say it on the LED potentially, or more likely on the packet, or you could just look up the LEDs, the ones we use in the lessons that I teach. We just go to the manufacturer, we look up the code, and it will say what the wavelength is. It will even say probably what an uncertainty there might be on that. So you could do an uncertainty calculation with it. But if I said, for example, that this was now 1.8, so let's say, for example, that this was a 600 nanometers, for argument's sake. We're going to see if this comes out well or not, how good my guessing is at numbers. So let's say, for example, this was 600 nanometers. I could then, obviously I'm going to do that, I'm going to times it by the wavelength, I'm going to divide it by the speed of light. So we would be able to say that our energy times by the wavelength divided by the speed of light is going to give me Planck's constant. And if I got those numbers, so 2.88 times 10 to the minus 19 times by 6 times 10 to the 7, so minus 7, that's my 600 nanometers, divided by the speed of light, 3 times 10 to the 8, will give me 5.76 times 10 to the minus 34, okay? 5.76 times by 10 to the minus 34. Now, obviously, I've actually literally just made these numbers up for this question. I mean, I chose some fairly sensible numbers, which is why I got a fairly close answer to what we know it should be 6.63 times 10 to the minus 34. But you can see how this works. Now, obviously, with a single measurement, there's going to be some significant uncertainties. I mean, there's uncertainties on the wavelength potentially as well. But yeah, I mean, I made the numbers up, which is why I'm a little way off. Really though, in A level, we know by now that we shouldn't be doing calculations like this of individual measurements. When you work out specific heat capacity, you don't use an individual measurement, you use a graph. The same thing goes here. So what we're going to do, instead of using an individual LED and one measurement to do the calculation, we're going to get a load of LEDs. So you tend to want a minimum of about 6 really, but you know, as many different wavelengths of light LED as you can get. You're going to repeat this and you're going to find out what the threshold voltage is each time. Now, we're going to be plotting a graph of voltage on the y-axis and 1 over lambda, 1 over wavelength on the x-axis. Now, the reason for this is because we can say, we know that the work done equals charge times by voltage. We know that the energy of the photon of light is equal to hc over lambda, and we know that these two equate to each other at the threshold voltage. So at the point that the electron only just does enough work to create a photon, we can say these two are equal to each other. So we say QV equals hc, and I'm going to write this as times by 1 over lambda. We know that Q is equal to the charge of an electron, so we're going to say that V is equal to hc, I'm going to bring that down, over E times by 1 over lambda. So if you create this graph here, you've got your y-axis is the voltage, the potential difference, your x-axis is 1 over the wavelength, and your gradient here, your gradient is going to be equal to hc over E. Okay, so you can then work out, we know what C is a constant, it's the speed of light. We know what E is, it's a constant, it's the charge of an electron, 1.6 times 10 to the minus 19. So you can then work out what H is from the gradient of your line. Okay, it's as simple as that.